Okay, so let's go over the result one by one. So first I am discussing about the result grid independence test. So here you can see, okay. So when we do simulations, we divide the fluid region into small parts, called grids or meshes. But how do we know which grid size is the best? To decide, we perform a grid independence test. First, we calculate the average velocity, and after it, average velocity for different grids size. To find the average velocity, we take the area under the velocity time curve and divide it by the total time. Okay, this gives us a single value of average velocity of each grid. Okay, then we plot a graph of average velocity versus grid size. So you can see here in this graph. After it, so what happened in the graph में क्या हो रहा है basically? So at first, the average velocity changes a lot as we make the grid size finer, a smaller size. Okay. Second, after a certain grid size, the average velocity doesn't change even if we refine the grid further. So this point where the result become constant is called the grid independent size. We select the size for our simulations because it gives accurate results without making the simulations unnecessary, complex or so. So here we found that the mesh size is 2186. Okay, so now we are going to the another result which is streamlines at t is equal to 30 seconds. So here streamline show the paths that fluid particles follow. They give us a clear picture of how the fluid flow around the object. In the streamline plot for 30 seconds, you can see the fluid flow smoothly at first, but separately as it passes around the object. Here you can see. Here you can see. First is come, and after it separates. Behind the object, vortices like circles flow, you can say circular pattern, uh, circular flow pattern are formed. These vortices are area where the fluid spins because of the separation and instability. Also, you can say the streamlines are helpful to visualize flow behavior, such as the regions of smooth flow, separation, and turbulence. Okay, so go to our next result, which is vector plot, or also you can say velocity vector plot for time is equal to time at 30 seconds. The velocity vector plot shows the direction and speed of the fluid at different points. What does the plot tell us? The around indicates the direction of flow, while the color of the arrows represent the velocity. Red arrows means the fluid is moving fast. Okay, here you can see here is a dancing part, and the blue arrows mean the fluid is moving slow. Behind the object, you can see the vortices again, where the arrows form circular pattern, just like this, just like this, and just like also this. This confirm that the flow separately and rotate in those regions. This plot helps us see both the speed and direction of the flow at a glance. giving more details about the flow behavior than the streamlines alone. Okay, so go to the our fourth result, effect of Reynolds number on coefficient of lift. Okay, so first of all, you know the Reynolds number formula, rho b dy mu. Here, the Reynolds number Re tells us about the nature of the flow, whether it is smooth, laminar, or chaotic turbulence. It also affects the coefficient of lift, how much lift force is generated. If I say what happens as increases, then we can say at low the lift coefficient increases steadily because the flow is stable and smooth. At a critical point around, the flow become turbulent. After this, the lift coefficient is starting to decreases. Here you can say this is increases, increases. After you can see decreases. Okay, because the turbulence causes energy loss and instability. This information is useful for designing things like airplane wings, where maintaining the lift is important. Okay, so next we are discussing about effect of Reynolds number on the coefficient of drag. So basically, so what is drag? Drag is the resistance an object feel when fluid flow over it. So how does Reynolds number affect the drag? As increases, the drag force also increases. So this graph, you can see here, this graph shows that the increases is not for perfectly straight but slightly curved, meaning drag rises faster at higher. And also you can say this happen because the higher corresponds to much turbulence, which increases resistance. Uh, Understanding drag is important for making object more aerodynamic and energy efficient. Okay. Go to the our last grade, effect of Reynolds number on Stroll number. The Stroll number is related to the frequency of vortex shedding. Vortex shedding happens when the fluid separates behind an object, creating alternating swirling pattern. So first of all, we know that the formula of Stall number F into D upon V, where F is a vortex shedding frequency, D in our case we can say D is equal to L and L is the characteristic length. V is the velocity of fluid and S T is the Stall number. So here here the size of the object, uh, what happens to as increases at first increases slowly, you can see here. After it, then it increases faster in the middle of the range, you can see here. And lastly, finally the increase slow down again at a very high. The change in the helpers understand the patterns of vortex shedding, which is important for preventing vibration or structural damage caused by these swirling flows. If I talk about its summary, then we can say the grid independent independence test ensure that here you can forget this. Okay, ensure that we use a grid size that is both accurate and efficient. And second, you can also say streamlines and velocity vector plots help us. What help us? Help us visualize. Visualize what? Uh, how the flow moves. Yeah, fluid moves, and also uh, including flow separation, separation and vortex formation, vortex formation, formation, and lastly, Redol- Reynolds number effects. You can say on first we can say uh, it affects on lift, drag, and vortex shedding. As we can say, no? Vortex shedding. So if you can say lift increases with until turbulence, turbulence reduces it. First, second, we can say drag rises with following a curved trend. Following a curved trend. You can say here drag if I want to talk drag. This is also we can say this is a linearly vary, and also lastly the total number increases with what showing changes in vortex shading frequency. Finally, we can say also this analysis help us understand fluid behavior and improve design. We can say improve improves design designs in where engineering application. Mm, application application like airplanes, airplanes we can say, also we can say cars and turbines you can say. So thanks.